Okay, so we're back, and what I'd like to do is a problem that kind of encompasses all that we've been talking about so far. So it's a typical problem that if we understand this problem, I think you're going to have all of the basics down, and you're in pretty good shape. So what we got here is a 10 kilogram block. I always like to use 10 kilograms because it's nice and easy. The numbers work out great. And we got a rope attached to it and pulling the block at 30-degree angle, and it's 100 Newton force that's pulling in the rope. And we're going to talk about friction here because we've got friction with the surface, and we said that the coefficient of kinetic friction, which is this mu sub k, is equal to 0.2. So this is obviously going to be in motion, and let me give you some particulars. We're going to say that it starts from rest. So it starts from rest, which means that our initial velocity has to be 0 because it starts from rest. And sometime later, force is going to be constant here, 100 newtons. Sometime later, the block is going to be some ways down the path over here. Again, we're still pulling with 100 Newton force, and it's still going to be at 30 degrees, but sometime later, it's going to be a certain distance away, and our job is to find that distance, and we're going to use the work energy theorem to compute the distance that this block moves. So we're going to be told that over here, so VI over here is 0, so here's your start, and at your start the initial velocity is 0 because it's starting from rest. Over here where we're going to finish, or we're going to look at it and say how far did it go in the time it took to get the speed or the velocity up, that's final velocity now, to 3 meters per second. Okay, so we start out at 0 meters per second because it's at rest. Someone's going to pull it with 100 Newton force at an angle of 30 degrees. It's going to be pulled through a distance d, and a certain time later it's going to have at distance d the final velocity is going to be 3 meters per second. We want to use the work energy theorem. So what's the work energy theorem? The work energy theorem tells us that the network, in other words, the work done by all of the forces, every force could be possibly doing some work, and the total work done by all of those forces on the object is the network. That's going to be equal to the object's change in kinetic energy. Now, the change in the kinetic energy of an object is the final kinetic energy minus the initial kinetic energy, because that's what the delta means. Delta means change. You're talking about always some final number or value minus some initial value. So in this case, we're talking about kinetic energy, and so we're going to look for the change in the kinetic energy. Kinetic energy, by definition, is 1/2 mv squared. So let me put up here. Kinetic energy is 1/2 the mass times the velocity squared. And that square is just the velocity, okay? So the final kinetic energy is going to be 1/2 the mass times the final velocity squared. The initial kinetic energy is going to be 1/2 the mass times the initial velocity squared. And that whole thing is going to be equal to the total or net work done on the object by all the forces. So that's just something on the side that we want to keep for definitions. Let's go back to our problem. One of the things we want to do, first things we should do besides putting down all our data, is to draw a free body diagram. So let's go back and do a free body diagram, and I'm going to put them in some different colors. So we've got the object's weight, obviously down. And the weight is little m g. So let's calculate the weight. 10 kilograms times little g is 9.8. 10 times 9.8 is 98 newtons. And you all should know that by now. That if I use 10 kilograms, it's 10 times 9.8, so the weight will be 98 newtons. Now we also have the normal force, which is the force due to the floor. They're the surface that the block is sitting on. Now, if there was no other forces, if this 100 Newton force was not here, this N, or normal force, would be exactly equal to the weight, because the system's balanced, it's in equilibrium, and the up forces, the total forces up, have to equal the total forces going down. So that's what we want to consider. However, in this case, we've got this 100 Newton force is lifting a little bit up because it's at a 30-degree angle, and if we resolve this 100 Newton force into its components, so this 100 Newton force is going to have a vertical component and a horizontal component. Now what's our horizontal component here? Well, it's going to be 100 cosine 30 degrees. This component is going to be 100 sine 30 degrees. So this guy here is equal to 86.6 newtons, and this guy here is equal to 50. Now you can see what happens is we've got the forces up are N, but we've also got this 50 Newton force heading up too. So we got the normal force from the floor, plus we've got the 50 Newton force. We've got these two combinations. They have to add up together and balance out the weight, which is 98 newtons. So in this case, you see what happens is that the normal force is not 98 newtons, it's actually 48 newtons from this equation. So the two forces, the normal up plus the 50 up, have to balance out or equal the 98. So when we do that, we solve for the normal force. Once we do that, we can find the force of friction, can't we? Because we know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So once we have the normal force, we can get the force of friction, because we're given the coefficient of friction is 0.2. So let's do that. So we got 0.2 times 48. And what is that going to do for us as far as friction is concerned? I think I did this before. Yes, it's 9.6. So this is 9.6 newtons. That's friction. So which direction is friction? Friction's going this way, opposite to the motion. So here's our force of kinetic friction, and that we're going to say is 9.6 newtons. So there's my free body diagram. I got my force of kinetic friction is 9.6. I've got the force component parallel to the floor from the 100 Newton force, which is 100 cos 30, which comes out to 86.6 newtons. And then I've got two forces up and a force down. But now look, the forces upward balance the forces downward because the block isn't moving up or down, see? It's only moving left, right. So these cancel out. So if you add the weight plus the normal plus the 50, and you consider their directions, that all those vectors, the sum of all three of those vectors is going to add up to 0. So the only two vectors that are going to be left, that are going to be considered in this problem, are the friction vector and the component of the 100 Newton force that's horizontal. And so we're going to have then the total force, which is the net force on this block, is going to be the 86.6 Newton force from the rope component minus the force of friction, which we said was 9.6 newtons. So the total net force then, in this case, is going to be, what did we calculate this out? I think we calculated out 77 newtons. And I'm going to stop this video here, and we're going to pick this up in the next video because I think we're running out of time.